Hi all. In the previous lectures, we have learned the mathematical modeling of mechanical, translational and rotational systems. So in this video, we are going to learn the mathematical modeling of electrical systems. As we know, the models of electrical systems can be obtained by using resistor, capacitor and inductor. So the current voltage relation of the resistor, capacitor and inductor is shown in this table. You can see it. And for modeling an electrical systems, the electrical network or equivalent circuit is formed by using this resistor, inductor and capacitor along with some voltage and current sources. So the differential equations governing the electrical systems can be found by writing Kirchhoff's current law equations by choosing various nodes in the network we have given. Okay. We have all learned the Kirchhoff's current and voltage law in the previous classes. So based on that, we can formulate the differential equations governing the system. And also the transfer function can be obtained by taking Laplace transform of these differential equations and rearranging them as a ratio of output to input. So in this table you can see that the voltage across the element resistor, okay, the equation for voltage across the element resistor is V of t is equal to R into I. That we know, that is V is equal to IR formula. Okay, V is equal to R into I, and also I is equal to V by R. Okay, and for an inductor, the voltage across that inductor, we know that the equation is L into di by dt, and the current flowing through that inductor is, equation is I is equal to 1 by L into integral V of t into dt. And by considering the capacitor, the voltage across this capacitor can be written as V is equal to 1 by C integral I of t dt, and the current flowing through the capacitor can be written as I of t is equal to C into dVt by dt. Okay, so these are the basic equations, that is voltage and current equations for the basic elements we are using in our electrical system. So we have to use these equations for formulating the differential equations of the governing system, okay, of the given system. And here, so this is our problem, that is the obtain the transfer function of the electrical network shown below. Okay, so it is a very simple network, and you can see a voltage source E of t here. E of t is applied to the network, and R1 is the C1, R2 C2 and V2 of t is the output. Okay, from the figure we understand that V2 is the output and E is the input. So we have to find the transfer function. So of course the transfer function will be V2 of s, that is Laplace transform of output by Laplace transform of input, that is V2 of s by E of s. So we have to find V2 of s by E of s from this network. Okay, so by observing this network, we know that two nodes are there, that is node 1 and node 2. So by analyzing these nodes, we can obtain different differential equations, and by taking Laplace transform and rearranging it, we obtain the transfer function V2 of s by E of s. Okay, so first we are considering the node 1 here, and we are writing the equation for the node 1, that is for the node 1, here we are assuming that the voltage at node 1 as V1 and voltage at node 2 as V2. Okay, just we are assuming these values. So we are taking the node 1, and by applying the Kirchhoff's current law here at node 1, we are applying the Kirchhoff's current law. So based on the Kirchhoff's current law, we know that the current flowing through this path, okay, through this resistor R1 can be written as V1 by E of t by R1. Okay, V1 by E, V1 minus E by R1. Okay, and also the current flowing through this capacitor can be written as C1 into dV1 by dt, that is we know that from the previous slide. That is, from this we know that the current flowing through the capacitor is C into dV by dt. So we are applying here. Okay, so C1 into dV1 by dt. Then current flowing through this path will be V1 minus V2 by R2. Okay, and we know that Kirchhoff's current law defines that the current entering the junction equal to current leaving the junction. So based on that we are writing the equation. So this is the node equation 1. Okay, equation for node 1, that is V1 minus E by R1 plus C1 into dV1 by dt plus V1 minus V2 by R2 is equal to 0. Okay, so by rearranging these equations, we know that we obtain V1 by R1 plus C1 into dV1 by dt plus V1 minus V2 by R2 is equal to E by R1. Okay, we have just rearranged this equation and we obtain a value here. Okay, and we are going to take the Laplace transform of this equation. Okay, we obtain as V1 of s by R1, that is the Laplace transform of the first time. Okay, that is V1 of s by R1. Then by taking the Laplace transform of the second time, that is C1 into dV1 by dt. So it is C1 into s into V1 of s. So here we are treating the initial conditions as 0. Okay, 0 initial conditions while taking the Laplace transform. So the second time, the Laplace transform second time is C1 into s into V1 of s. So here it becomes V1 of s by R2 and minus V2 of s by R2 is equal to E of s by R1. Okay, and we are taking outside V1 of s from these three times. We obtain the first equation like this. Okay, so by observing the first equation, we know that here the variables are V1, V2 and E. We must obtain, that is the transfer function as V2 of s by E of s. Okay, so both terms are here, but another variable V1 of s is also here. So we have to replace this V1 of s in terms of V2 and E. So for that we are going to the next node, that is node 2. Okay, by analyzing the node 2. Okay, this is the node 2. Okay, by analyzing the node 2 we obtain the equations as, okay, the current equations as, that is V2 minus V1 by R2 plus C2 into dV2 by dt. Okay, C2 into dV2 by dt, that is here we can see that is at node 2 V2 minus V1 by R2 plus C2 into dV2 by dt is equal to 0. Okay, so this is the equation for node 2. And also we are taking the Laplace transform here, that is V2 of s by R2 minus V1 of s by R1 plus C2 into dV2 by dt. So it becomes C2 into s into V2 of s is equal to 0. Okay, and also we are just rearranging that. We obtain V1 of s, that is V1 of s by R2. V1 of s by R2 is equal to V2 of s by R2 plus C2 into s into V2 of s. Okay, and from these two terms we are taking outside V2 and we obtain equation like that. Okay, and just rearranging that, we will obtain V1 of s equal to 1 plus SC2 R2 into V2 of s. So this is the equation 2. Okay, and we are going to substitute this the value of V1 in, that is equation 2 in equation 1. Okay, and in the previous case I have said that the variable here is V1. Okay, so we have to replace this V1 in terms of V2 and D. Okay, so here V1 is equal to 1 plus SC2 R2 into V2. So we are just substituting this value here. Okay, instead of V1 we are just substituting this value. So the equation becomes, instead of V1 this value will come here and remaining values are there. Okay, and also just we are rearranging the terms. Okay, rearranging the terms and taking outside V2 of s. Okay, while rearranging you should careful. Okay, mistakes may be there, so you should careful while rearranging the terms. So from this we obtain the transfer function as V2 of s by E of s. V2 of s by E of s as R2 divided by 1 plus SC2 R2 into R1 plus R2 plus SC1 R1 R2 minus R1. So this is our final answer, that is the transfer function of the electrical network given in the question. Okay, so I hope all it's very clear, all of you understand it well. Okay, thank you.